So, lesson 5, one-dimensional momentum and impulse. By the way, actually, I know I'm starting a new unit. Why didn't you call this lesson 1, Mr. Dueck? It's because I took this unit on energy and momentum and split it up into 2 components. So, although this is a continuation of unit 3, I'll call it unit 4, but it's lesson 5, not lesson 1, because I just haven't got around to changing the numbering. One of the most important concepts in physics is the idea of momentum. Newton first used the concept when he phrased his second law of motion. Newton never actually said F equals ma. Logan, he phrased it differently. He was much less interested in acceleration and much more interested in momentum. He called the product, I guess we're going to multiply, of mass and velocity quantity of motion. But over the years, this product has come to be known as momentum. It's the amount of motion an object has. What makes momentum so important is that, like energy, it's conserved. It's a conserved quantity, which is why these are part of the same unit. In an isolated system where there's no external forces or sources of energy, the total momentum of the objects will remain constant. The total momentum before an event, Jake, will equal the total momentum after the event. This is called the law of conservation of momentum. And in some ways, it's better or more accurate than the law of conservation of energy, because often we've had to, McKinley, in our energy section, ignore friction and heat and other sound and other dissipative energies. Momentum, we can be more accurate, but it's trickier because it's a vector, and we're going to be doing trig like you wouldn't believe. So, any moving object has momentum. So if you're not moving, no momentum. Momentum, now we can't use m for momentum because m is taken for mass. So because it's a product, we use the letter P for momentum. It's calculated by multiplying the mass of the body times its velocity. It's equal to mass times velocity, and I'm going to put a vector over the P equals m, and I'm going to put a vector over the v. And you're going to start to notice that I'm emphasizing vector notation much more over the next few lessons, and it's to remind myself, Logan, this time direction matters, direction matters, direction matters, direction matters, direction matters. I can't emphasize that enough. What would the units be? What do I measure mass in? Kilograms. What do I measure velocity in? Meters per second. The units for momentum are kilogram meters per second. They haven't shortened it, although, Kyle, there is a movement afoot to rename that an Einstein, but it hasn't happened yet. Just like a Newton is a kilogram meter per second squared, just like a joule is a force times a Newton meter, momentum is kilogram meters per second. They may rename that an Einstein in your lifetime, I don't know. Again, momentum, Rachel, is a vector quantity, and the direction of the momentum vector is actually the same as the direction of its velocity vector, because mass is a scalar. If you know the direction of the velocity, Holly, you know the direction of momentum. And what that means is if you add momenta, which is the plural of momentum, we're going to be doing vector addition. We're either going to be going one way's positive, one way's negative, if everything's in a nice straight line, or if we have angles, Emma, we're going to be adding stuff tip to tail, tip to tail, tip to tail. In fact, Newton's second law can be rewritten in terms of momentum. So Newton's second law is F equals ma, which is really m change, oh, that's not right, change in velocity over time, change in time. That's the definition of acceleration, a change in velocity over a change in time. What's change in anything? So I can actually rewrite this as m v final minus v initial all over delta t. change in time. I can now go dunk, dunk, and I'll get mv final minus mv initial all over change in time. What's mass times velocity? What did I just say on the line above? In the box above, sorry, in the box above. What's mass times velocity? Momentum. So what's mass times velocity final? Momentum final. And what's mass times velocity initial? Momentum. So I can really write this as F equals momentum final minus momentum initial. By the way, I should have been very careful and put vectors above the velocity there, and I should have put a vector symbol there, and I got to be way more careful with my vector notation. Over change in time. And what's final minus initial the same as? Change in. In other words, Logan, I told you earlier that Newton never said F equals ma. What he actually said was force is equal to the change in momentum over the change in time. Which is, come here, which is F equals ma in disguise if you work your way backwards enough. Okay? So Newton's second law can be stated in words in terms of momentum as follows. If you have a force, if you have an unbalanced or net force, because two forces cancel each other, but if you have an unbalanced or net force acting on a body, that changes its motion so that the rate of change of momentum is equal to the unbalanced force. Remember I said anytime there's a rate of change, Justice, that means you're dividing by time. You want to know how fast the momentum is being changed? Oh, it's equal to the force in newtons. Sorry, the unbalanced force in newtons. Got to be careful. Next topic, impulse. If the equation for net force that we just derived is rearranged by multiplying both sides by delta t, in other words, if I go back here and if I move the delta t up to there, because stuff moves diagonally, we get F delta t equals change in mv, which is change in momentum. And in fact, that's another word for impulse. Impulse means change in momentum. And this is one that bugs me because I'm going to be using the word impulse all throughout the unit, and kids are going to freeze up. What does impulse mean, Vanessa? Change in momentum. What's another word for change in momentum? Impulse. When you see the word impulse, what can you say instead? When you see the word change in momentum, what can you say instead, Holly? Impulse. Oh, let's put it all together. And what's change in anything? In other words, every year on your test, on your momentum test after Christmas, I'm going to ask you to find the impulse, and kids leave it blank. No, it's the change in momentum. Find the final, minus, find the initial, subtract, and you're done. But kids forget that impulse is a synonym for change in momentum. It's not a synonym for momentum. Impulse means you have a change in momentum. Those of you that are Star Trek fans may recall Star Trek talks about the impulse engines. They're changing the momentum of the ship. They're causing it to speed up or slow down because they're not changing its mass. A given change in momentum can be produced by a large force acting for a short time, like an explosion, or by a small force acting for a long time. So we're looking in terms of space travel. One possibility is something called an ion drive, which literally spits out the back end of the spacecraft small charged particles which have almost no mass. But if you keep doing that for a long, long time, you're going to gradually exert a big change in momentum because, well, you can either, if you look at the equation, have a big time or a big force. Now, the biggest change in momentums are big forces combined with big times. We'll talk about that. The units, so momentum has measuring units which have the dimensions of mass times velocity, which is kilogram meters per second. Impulse has the units of force times time, which is, well, force, Newton, time, seconds. However, so Newton seconds, force is what times what, the most basic definition that we've been flogging for a while. So this is really the same as mass times acceleration times seconds. There's the newtons. There's the Newton seconds. And Ryan, can you see that I could cancel out one of the S's and I can say, oh, you know what? Newton seconds is interchangeable with, or is the same as, kilogram meters per second, which is another way, Rachel, to say they're both momentum. Force times time, if you muck around with the units, actually gives you kilogram meters per second, mass times velocity. Which one is correct? They both are. Generally, if I'm finding an impulse and I've used force, I'll write my answer in Newton seconds. If I'm finding an impulse and I've used MV, I'll write my answer in kilogram meters per second. If I'm not finding an impulse, Sam, if I'm just finding momentum, I'll write my answer as kilogram meters per second. But I won't take marks off if you use one or the other. I'm not that fussy. The law of conservation of momentum. The total momentum of an isolated system of objects will remain constant. Tie that doesn't seem profound, oh, it's hugely profound. This is going to allow us to analyze collisions and explosions, car crashes and blowing stuff up. I just saw you get a little smile there. Oh yeah, it's cool stuff. Example 4. Turn the page. Momentum is what times what? The basic definition, mass times velocity. You know what? Since you've all turned the page, let's write that at the top. This is on your formula sheet, but we're going to be using it a whole bunch on this. Momentum is mass times velocity. Okay. So example 4 says this. If conditions are such that the car and the truck end up at rest after the collision, how can we say that the momentum has not been lost for the system? Because before the collision, they both have velocity. After the collision, they have no velocity. What's the momentum after the collision? How fast is the truck moving after the collision? 0. How fast is the car moving after the collision? 0. What's the momentum after the collision? Momentum. You okay with that? Logan, you okay with that? Since momentum is mass times velocity, and after the collision, velocity of each is 0, momentum is 0. Here's what that means. The law of conservation of energy says that before the collision, the momentum must have been 0. No, Mr. Dueck, that's impossible. They're moving. Can anybody tell me how it's possible for before the collision, the momentum to have been 0? Same momentum because they cancel each other out? I don't think they had the same momentum. I think you're thinking it right and saying it wrong. They can't cancel each other out if they have the same momentum. They can only cancel each other out if they have, I'm looking for a word that begins, what? Opposite momentum. Why? Momentum, scalar, Ryan, or vector? Vector. So watch. Before the collision, we have momentum of the truck, vector sign, plus momentum of the car, vector sign. Wham! They collide. After the collision, we have no momentum. So we have to be able to prove that before the collision, we have no momentum. Momentum is what times what? And I'm very careful. You'll never, ever, ever, ever hear me say mass times speed. That's wrong. It's mass times velocity. Okay, so what's the mass of the truck? 2,400. What's the velocity of the truck? 10 plus. What's the mass of the car? 1,000. What's the velocity of the car? 24 is wrong. Negative. We have to take direction into account now. And you get 24,000 to the right plus 24,000 to the left, or negative 24,000. And you do get a final momentum and an initial momentum of 0, of zip, of zilch, of nada. So this is possible. The law of conservation of momentum can be written in several ways. Okay? Have you guys seen this symbol? Don't write that down. Before, the summation symbol? You have or no? A little bit? It's, by the way, on a typewriter, it looks like this. But over the years, it usually becomes kind of a capital M on its side because we're kind of lazy. This means total, or the sum of. So here's how you can write this. In English, the total initial momentum equals the total final momentum. Too much writing. Momentum 1 initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final. Still too much writing. The sum of all the momentum before, or initial, equals the sum of all the momentum final. You know what? This is the one that I write down every time because it's the least amount of writing. It's the best bang for my buck. I know it's using some funky notation, but I like it because I can adapt it to anything. This is not on your formula sheet, but Josh, this is the free body diagram equivalent of momentum in that, if they're not talking about impulse, when in doubt, I write this down and then I go from there. You can also say, since momentum is mass times velocity, you can take this first long one and turn it into m1 v1 initial plus m2 v2 initial is m1 v1 final plus m2 v2 final. I like the one in red. We use conservation of momentum, this in red, whenever there is a collision or an explosion. In fact, here's my joke. We use it whenever there is a jeune. Collision, explosion. So, change in height, change in speed, yucky curvy path, conservation of energy. Forces and friction and acceleration, free body diagram. If you got a collision or an explosion, and they don't specifically mention the word impulse, it's probably a job for conservation of momentum. Example 1. A rifle bullet of mass that leaves a muzzle with a velocity of that. If the 3-kilogram rifle is held very loosely, with what velocity will it recoil when the rifle is fired? What are they asking me to find here? What are they asking me to find here? Grant, what are they asking me to find here? Velocity or speed? So that suggests a vector approach, velocity. This is a momentum question. Also, I think firing a gun, that's technically an explosion. So I'm going to write this down. The sum of all the momentum before the explosion equals the sum of all the momentum after the explosion. Really what we're talking about is this. The momentum of the rifle initial combined with the momentum of the bullet initial has to equal. So we have a rifle, we have a bullet. We pull the trigger. Bang! After the explosion, what's moving? The rifle, the bullet, or both? I think both. Stuck together or separate? Momentum of rifle final plus momentum of bullet final. Before you pull the trigger, what's moving? The rifle, the bullet, both, or neither? Meant to be really obvious. Neither. So what's my momentum before grand total if nothing's moving? If one of them had been moving, I could easily put mass times velocity. We pull the trigger, bang. After we pull the trigger, what's moving? Both. Stuck together or separate? Separate. Okay, I have a letter P with a vector, a momentum. Momentum is what times what? What did we write at the top of the page for a good reason? So this is going to be mass of the rifle V final of the rifle plus mass of the bullet V final of the bullet. We are, Ryan, going to be using lots of subscripts, but we're going to try and be very, 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 very clear. What did you say we're trying to find, Grant? Which one? Which one? Help them out, folks. Which one? Rifle. Why? Because they gave me the bullet velocity. Can you help, Jake, could you help Grant out and show him where the bullet velocity is in the question? He's having a little trouble. Thank you, Jake. You are so good to help him out. You can switch back to your regular chair now, Grant. Are there angles mentioned in this question, or is everything in a nice straight line? Okay, if there were angles, we would now dolp, tip to tail, and vector. Since everything's in a nice straight line, we'll just let one way be positive and one way be negative. In fact, I think what I'm going to do is I'm going to say this. Negative MR VFR equals MB VFB. I'm going to subtract the rifle over to the left-hand side. Grant, what did you say we're trying to find? Velocity of the? Let's get the rifle velocity by itself. What's in front of it, Grant, my friend? So how would I move the negative m over? So the final velocity of the rifle is going to be mass of the bullet, velocity final of the bullet, vector, divided by a negative sign and a mass. By the way, suppose the bullet was heavier. Would you recoil more or less or the same? If m of the bullet got bigger, what would happen to the velocity of the rifle? Bigger, smaller, or stay the same? If this gets bigger, bigger. It's going to recoil. This is why firing a shotgun has more kick, say, than firing a .22. Or if instead of having a bigger bullet, we added more gunpowder so that the bullet left faster, you would also get bigger recoil. This explains tanks and artillery guns and how that all works. Or you can get less of a recoil by having a heavier rifle. Explains what a tank. One of the reasons a tank has so much mass is absorb the recoil from that horrendous forward thrust of the shell. Let's plug and chug. Mass of the bullet, 0.06, 60 grams. Velocity, 600, divided by a negative sign and 3 kilogram. Okay, how fast will this rifle recoil? Divided by -3, you get -12? And then you would absorb that with your shoulder by giving with it and taking its kinetic. Now it also has kinetic energy. You'd absorb that in your shoulder. You might get a bruise after a while. Turn the page. Football. Tackling is a collision. What is the momentum of a 112 kilogram football player running at 4.8 meters per second? Jake, momentum is what times what? So it's going to be mv vector, 112. By the way, this isn't a collision yet or anything, so I'm not freaking out. I'm just plugging and chugging, times 4.8. And I tried to make this about right. 112 kilograms, it's about a 270-pound lineman. And 4.8 meters per second, that's not that fast. That's about what they get up to. So, okay. Or this could be one of the big bruising running backs you see in the NFL. There's those guys that weigh 250, 260. 112 times 4.8. I think Gronkowski is, as a tight end, is 265 or something. It's about 100. He weighs about 112 kilos, give or take. You get 537.6. I'm going to say 538. 538 what? Units. Kilogram, meters per second. Good. Good. B. Logan, what's B asking me to find? B, not C. B. Impulse. What's another word for impulse, folks? It's change in momentum. First thing I'm going to write down is this. Okay? Now, I have two ways to do this. I can either go, don't write this down, because we did say that. Or I can just use, hey, what's change in anything always? Final minus initial. Now, I would use this one if the question had given me a force or a time. Logan, what did you say that they want us to find in part C? So you know what? I'm not going to use this right now. In fact, I think what I'm going to do is I'm going to come back to that for part C. So, hey, Ty, what's change in anything? This is going to be momentum final minus momentum initial. And Ty, what if you write at the top of the page? Momentum is what times what? This is going to be mv final minus mv initial. And hey, what is the final velocity, Logan, in part B? Got to read the question and do a little bit of thinking, but I think you'll get it. What's the final velocity? Here's your hint, kiddo. 0. So what's his final momentum? If momentum is mass times velocity, what's mass times 0? Okay, so this is going to be 0 minus, and mass times initial velocity, we just did up here, 538. So a little football physics for you guys. To bring this person to a stop, you would need to give him an impulse of negative 538 kilogram meters per second. Now, that assumes you hit him head on. What if you hit him at an angle? We'll get there, but in a couple of lessons. But if you hit him head on, you've got to give him negative. What's the negative saying? In the opposite direction that he's running. Okay, so here's your head-on tackle. C. Suppose the tackle is completed in 1.2 seconds. So this is not a bruising instant tackle. This is, you've grabbed onto him, but the running back is churning forwards, and it takes about 1.2 seconds to bring this person to a stop. Kind of a Marshawn Lynch tackle for those of you that are Seattle fans. What average force? So Logan, you pointed out they're asking me to find force. And what did you say they asked us to find in part B? Is there an equation that has force and impulse in it? Yep. This one is on your formula sheet. In fact, I think the only two equations in this whole unit on your formula sheet are that one that I just wrote in black and the one that I wrote in blue at the top of the page, this one here. I think that's it. Anybody got their formula sheet handy? It's just the two, right? All it is going to be then is applying it. Okay. Logan, what did you say they're asking us to find in part C? How would I get the F by itself, folks? Divide by delta t. Okay. So force is going to be the change in momentum divided by the change in time. We just figured out the change in momentum, negative. This time I'll bring in the 500 and, what did I say it was? 537.6, I'll use the full value, divided by 1.2. I'm going to get a negative answer. What's the negative telling me? The direction of the force has to be in the opposite direction that this person was what? Running. Okay? Oh yeah, football for you. So football physics. I'm looking around trying to catch my football player people. Negative answer button divided by 1.2. Negative 448 newtons. Yep. By the way, yes, force is change in momentum times change in time. Force is also mass times acceleration. If you're a heavier lineman, bigger mass, you don't need to have as big an acceleration to bring this guy to a stop. If you're a smaller person, cornerback, you better be moving to bring this guy to a stop, otherwise you're going to be in trouble. Example 3. You're doing a spacewalk outside the space shuttle, and there's no cable between you and the shuttle. You're using the little jet pack, well, rocket pack. It's not a jet because a jet sucks in air. Rocket pack. Your small maneuvering rocket pack suddenly quits on you. Uh-oh. And you are stranded in space, but you're also holding a $50,000 camera in your hands. Oh, they're all expensive. You got to realize any electronic components in space has to be able to handle about minus 150 degrees and about positive 150 degrees, depending on whether you're in the shade or in the sun. It's really hard in electronics. Anyways, what will you do to get back to the shuttle? Well, first thing you would do in real life is you would radio and somebody else would come and get you with the spare rocket pack, which I'm sure the shuttle has. In fact, I'm sure the shuttle had 3 spare rocket packs, a backup for the backup. But let's assume that that's not an option. This is a physics thought experiment. How could you get back to the shuttle? Yeah, Vanessa. So orient yourself so that maybe your back is to the shuttle. And if you push the camera, right now, before you push the camera, what's the momentum of you and the camera? 0. If you push the camera forwards, giving it a mass times velocity, you're going to pick up a mass times velocity in the opposite direction. Now you have a bigger mass than the camera, smaller velocity, but in theory, you should be able to drift there. So, quickly push the camera away from the shuttle. And then explain to NASA why you don't owe them $50,000, right? But actually, this is how rockets work, and this is why they work in outer space. All rockets do is they expel mass out the back. Fuel, gas particles, air, whatever. Gas. And because there's mass going backwards times velocity, momentum says you must also have mass times velocity going forwards. So a rocket expels 1.2 times 10 to the third, 1,200 kilograms of gas each second. And the gas leaves the rocket with a speed of that. Will the thrust produced by the rocket be sufficient to lift it if the force of gravity on the rocket is that there? Well, I guess the thrust, the force from the rocket engine has to be bigger than that number there. What are they asking me to find in this question? Well, I think that. What is that? What is thrust actually a measure of? That's a calculator, right, Ty? Okay, just making sure. For a second I thought it was a smartphone and I was going to freak. I think thrust is a force. So I think what they're asking me to find is that. Okay. What have they given you? A mass? I see a velocity. You know what? I'm looking for an equation that has force, mass, and velocity in it. You know what? I think what I want to use is change in momentum equals F delta T. By the way, this one's a bit tricky. What's the time value in this question? Read carefully. They snuck it in barely. 1 each what? Seconds. So I'm going to make a little note here. Delta T equals 1, which means on my next line, Emma, it's just going to vanish, because does timesing by 1 change anything? No. So, but I don't want you to think that somehow I just ignored it. I took it into account. Okay? So I have this. And change in momentum. What's change in anything? Before the rocket turns on its engines, how fast is the gas in the rocket engine moving? I think I can say this. It's not putting out anything before you switch the engine on. So what I'm really going to get is mass times velocity equals thrust. Okay? Now, I got to be careful. It's really mass times velocity divided by time. I just want you to make sure, because mass times velocity, F does not equal mv. F equals ma, but F does equal mv over t. So I'll put the time there just so that the units don't freak me out, because otherwise I'm somehow giving you an entirely new equation that's wrong. Force is not mv, but force over 1 second is mv. Okay? It's going to be the mass, 1200, times the speed, 5 times 10 to the 4th, divided by 1 second. I won't bother dividing by 1. Will this rocket get off the ground? So a little rocket science. Oh, I better double check. 1, 2, 3, 4, 5, 6, 7. You know what? The force is 6.0 times 10 to the 7th newtons. Gravity's pulling down at 5.8 times 10 to the 7th newtons. You know, there's a little bit of extra force left. In fact, if I wanted to, I could go winner minus loser. There's my net force. And if I divided that by the mass, I could find my acceleration. What's the mass? Not 1,200. The mass of the rocket would be, well, if that's the force of gravity on the rocket, that's mg on the rocket. I could divide that by g. I could figure out the acceleration if I really wanted to. We won't. Next question. A 3.2 kilogram cart traveling at 1.2 meters per second collides with a stationary 1.8 kilogram cart, and the two carts stick together. What's their common velocity after the collision? Okay. Ryan, what's this one asking me to find, kiddo? Common velocity. Is there a collision in this question? This is a job for conservation of momentum. So I haven't used that. I've been doing lots of impulse questions so far because they were talking about forces and times and okay. But now, first thing I would write, the sum of all the momentum before the collision equals the sum of all the momentum after the collision. And then I ask myself, before the collision, what's moving? Mass 1, mass 2. Oh, by the way, Sam, let's decide the first mass the question talks about is going to be mass 1. The second mass it talks about, Sam, is going to be mass. The only way I won't do that is if they give me a picture and they've labeled it differently. Then I'll go with what they've labeled it. But if it's an English question with no picture, okay. Before the collision, what's moving? Mass 1, mass 2, or both? Read carefully. Ryan. So it's going to be momentum 1 initial. Bam! They collide. After the collision, what's moving? Mass 1, mass 2, or both? Read carefully. Both. Stuck together or separate? Momentum both final. If they were separate, Rachel, I would have momentum 1 final plus momentum 2 final. Does this question mention angles at all? Is there any like north of south, east of west angles, anything like that? So I don't need to go all vectory. I'm going to let to the right be positive, to the left be negative. Momentum, let's keep going, Ryan, is what times what? So momentum 1 initial is going to be mass 1, V1 initial. Wham, they collide. Did you say they're stuck together? How could I show, oh, you know what? I think that's going to be mass 1 plus mass 2 in brackets V final. Because I'm going to argue if they're stuck together, they have to be going at the same velocity. That's the definition of stuck together. What did you say I'm trying to find, Ryan? In what I have here, what am I trying to find? How would I get it by itself? So the final velocity after the collision is going to be m1 v1 initial divided by m1 plus m2. Now before you start crunching numbers, you can. This is any kind of head-on collision. This is any kind of head-on collision. So what if we collided with a heavier object? What if the second object was heavier? If this number here was bigger, what would you expect from our final velocity? Bigger, smaller, or stays the same? Smaller, which you probably intuitively could have imagined. Oh, what if instead of hitting a shopping cart, what if the shopping cart ran into a car? It would hardly move. But okay, there's the physics behind it. Let's crunch an answer. Mass 1, 3.2, V1, 1.2, divided by 3.2 plus 1.8. Mr. Dueck, how come the carts don't have the same mass? Oh, first cart has groceries in it. (3.2) times 1.2 divided by bracket 3.2 plus 1.8. You get 0.768. Meters per second. Not a big fan of number 6. I keep meaning to change it and I keep forgetting, so cross it out. But let's do example 7. Okay. Hey, Ty, let's crash some cars. Okay. A 1.2 times 10 to the third kilogram car traveling 33 meters per second. That's about 100 kilometers per hour freeway speed. Collides head-on with a 1.8 times 10 to the third car traveling 22 meters per second, about 70 kilometers per hour, in the opposite direction. You know what? Since we're talking about vectors, Emma, and they mentioned that, I'm going to underline, I think that's going to be important. If the cars stick together, so the wreckage sticks together, what is the velocity of the wreckage immediately after the impact? Okay. Hey, what's this question asking me to find, Luna? What's this question asking me to find? I caught you mid-yawn. I apologize. Which is why I picked on you. Sorry.
Change in?
I don't see a change in. Read the last sentence to yourself. I think you'll figure it out. VF, the velocity. Is there a collision?
Yep.
This is a job for conservation of momentum. So I'm going to start out by going, hey, the sum of all the momentum before the collision has to equal the sum of all the momentum after the collision. And by the way, McKinley, you'll notice I'm not having to have a fudge factor like plus heat or anything like that. Momentum is trickier than conservation of energy mathematically, but it's also, by definition, more accurate. Before the collision, what's moving? Mass 1? Really? Working on homework at the same time? I don't know. What's moving? Mass 1, mass 2, or both? Both stuck together or separate before the collision? Separate? So I'm going to go like this. Momentum of the first car initial plus momentum of the second car initial. Bam! They collide. After the collision, what's moving? Mass 1, mass 2, or both? And by the way, if I'm sounding repetitive, this is going to get us through yucky, funky angles and explosions as well. So this is always going to be my approach. Stuck together or separate. So move after the collision. Mass 1, mass 2, or both. I think both stuck together or separate. Together. So it's going to be momentum, both, final. Then I always pause here and I say, any angles, any north of south, east of west, any thetas, any degrees. Okay, if there was, my next step, and we're going to get to that next lesson, would be to dulp, would be to draw a little picture. Here, I'm going to pause. Momentum 1, mass 1, V1 initial, plus mass 2, V2 initial, equals mass 1 plus mass 2, V final. Luna, what did you say they're asking me to find? How would I get VF by itself? Okay, so I'm going to get an expression. Nice. VF is going to be mass 1 V1 initial plus mass 2 V2 initial all over M1 plus M2. Oh, I like this question. I like this question. I like this question. What's mass 1? 1200? What's V1? 33. Plus, what's mass 2? 1800. What's V2? Negative 22. All divided by Now, we're going to be getting some fairly long, complicated equations in this unit as well, so it is well worth practicing on your calculator. Trust me. By the way, I went through your forces test with you guys on last week, right? Yeah, okay, making sure I did. Oh, what do you get? Okay, by a wonderful fluke, this collision exactly cancels out the momentum. These come to a stop. This would be a head-on collision. Boom! They would probably jump and stop. What if I had gotten a positive answer? That would mean that the wreckage would keep going in the direction of car 1. What if I had gotten the negative answer? That would mean car 2 had more momentum than car 1, and car 1 would change direction. Car 2 would keep going in the same direction, but way, way, way slower. Next page. Example 8, part A. What impulse must be imparted to a 145-gram baseball to change its velocity from 40 meters per second south to 50 meters per second north? Sam, what's this question asking me to find? Second word. Impulse. Okay, I'm not going to go the sum of all the momentum initial equals the sum of all the moment, even though, by the way, hitting a baseball bat is technically a collision. Since they said impulse, I'll start out there. Maybe I'll end up in the conservation of momentum law, but I'm going to start out by saying, well, impulse is change in momentum. Now, we have two ways to write this. Once you've written that down, put your pencils down and look up. I can go, Jake, what's change in anything? In fact, you know what? Momentum is what times what? Okay, so change in momentum is mv final minus mv initial. Can I do that in one step? Or I can go force change in time. Those are, anytime they talk about impulse, another word for change in momentum, Logan, those are my two options. Sam, looking at part A, am I going to use the one that has forces in it, or am I going to use the one that has two velocities in it? Can you see how you can figure it out? Okay, so just letting you know. You got to figure out which one you're going to use. Both are options, but you'll be able to narrow it down usually pretty easily. So pick your pencils up. This is going to be mv final minus mv initial. $145 grams, Sam, what's that in kilograms? Yeah, point is a good start. You go, absolutely, 0.145. What's the final velocity, Sam? $50 minus 0.145. What's the initial velocity, Sam? Nope. Why is he incorrect, folks? Sam, what word is that right there? What word is that right there? Okay, and I by the way, I like this question. I like this question. I like this question. Is there a change in direction? As soon as you said 50, you've just decided that north is positive. So what's the initial velocity? Not speed, velocity. Negative. This is a great multiple choice question, Sam, and you better believe one of the answers will be if you do it with a positive there, right? Absolutely. Okay. How much impulse did we impart to this baseball? By the way, 40 meters per second coming in. This is about an 85 mile an hour. I won't call it a fastball, probably a slider, but I tried to make these numbers reasonably accurate. And a baseball weighs around that. In fact, can you see, Sam, I actually get a minus, which is a, what we're saying is, by the way, what you have to do to stop this baseball, so instead of north, let's imagine it coming towards me this way. I first of all have to bring it to a stop, plus I need to get it to go that way. That minus gives me a bigger answer, because I've got to give it a pretty big change in momentum, as opposed to just changing it from 50 to 40. That would be if it was coming in at 40, to change it to 50, I just have to give it a little bit of a boost in the same direction it was coming in the first place, barely any at all. Does that make sense? Did you get, a typo apparently? How about times, Mr. Dueck? Do you get 13.05? I'll go I'll go 13.1. Units, kilogram, meters per second, because change in momentum is momentum. You could also say, Logan, Newton seconds. I wouldn't take marks off, but since I happen to use mass times velocity to find this impulse, I'll use kilogram, meters per second. Okay. You're turning the page to see how much more. Patience, we're getting there. Okay. Hey, Ben, what's B want me to find? B, what does it want me to find? Sorry, I didn't hear. Yes. By the way, what did we just find in part A? Impulse. I know F equals ma, but right now I'm also kind of thinking, hey, maybe I can use maybe my first guess might be to go impulse is also force times change in time. Ben, did they give me the amount of time that this collision occurred for in the question? Yeah, they did? Then I'm going to use this. I could, by the way, because I have an initial velocity and a final velocity, and I could go A equals VF minus VI over T and MA. You know what? The force is going to be the change in momentum divided by the change in time. It's going to be 13.05 divided by 1 millisecond. Milli is, anybody have their formula sheet? I think it's 10 to the negative 3. I have all them on there somewhere, right? Milli, 10 to the negative 3? Negative 2? I don't think so. Okay, 1 times 10 to the negative 3, divide by that. So it's going to be 13.05 divided by bracket 1 to the negative 3. 13,000 newtons of force. Is that big? Would you want to get hit by a baseball bat? That actually is not, I think that's a reasonable answer. 13,000 newtons. I think that's why getting hit by a baseball bat accidentally would hurt, or on purpose would hurt. Okay. How much more am I doing? Example 9. We're going to talk about eggs. Yep. I want to push through because my goal is to give you guys no homework over the Christmas break, so bear with me. Stop harassing Rachel. She needs to pay attention. I know. A 2,000 kilogram car traveling 15 meters per second rear ends another car of mass 1 times 10 to the third. The second car was moving 6 meters per second in the same direction. Yeah, you know what? Usually when you rear end somebody in a car accident, they were moving in the same direction as you, but slower. Or they were stopped. Rarely are they backing up on the road and you rear end them. People don't go in reverse on a road unless they're really out of it. What was their common velocity after the collision if the cars locked together during the impact? Could we handle this? Is there a collision? Yeah. This would be a job for conservation of momentum. Okay. Do you guys want to do this, or are you guys okay on this and you want to move on? Move on? I've done a couple of collisions already. Okay. Example 10. You can try that one on your own and compare answers. 2 eggs are dropped from a height h. 1 egg hits the floor and breaks. The second falls in a pail of water and survives. Why does the second egg survive? Convince me.
In the first one, that it stops, it comes to a stop instantly, and the second one, it has a.
So you know what? Let's try and do this a little bit more algebraically. No, I don't mind English explanations. I just hate writing them out. That's great if you do it. The fact that we're dropped, what's VI? 0, and what's VI? 0. Are they both falling the same height? So what can you tell me about their impact velocity? If we compare their impact velocities to each other, they are the... So you know what? Let's go also same VF. Egg 1 and egg 2 have same change in momentum. What's another word for change in momentum? Impulse. Why? Well, if they got the same mass and the same final velocity and the same initial velocity, hey, that's mv final minus mv initial. It's the same. What's another way to describe what's another equation? What's another way to describe impulse, though? Okay, so change in momentum equals F delta T. Right? Egg 1, its change in momentum is, what did you say, Atla? Egg 1's time of impact compared to egg 2? Okay, I'm going to do this. Little tiny delta T, huge F. Egg 2, same change in momentum, but it has a smaller F. Why? By the way, that's what seatbelts do. In every car accident, we're stuck in the same change in momentum in that your final moment, what's the final momentum of every car accident? 0. Same with the final kinetic energy of every car accident, 0. But now we're talking collisions. Initial depends how fast you're going. But look, if we can lengthen that time of impact, that dramatically can decrease the amount of force your body undergoes. So this is another way to think of what crumple zones do. We talked about crumple zones last unit, also absorbing kinetic energy, force times distance, but they also lengthen the time of impact. And so does a seatbelt. The seatbelt is designed to let you move forward a little bit and then jerk you to a stop. We'd rather have you crack a few ribs than die, but we can lengthen the time of impact. Oh, we're going to get through this, barely, but we are. So if we looked at a graph of force versus time for the egg hitting the floor, it'll look as follows. So here's the egg hitting the floor. Which of the following graphs, A, B, or C, would best represent the force of time for the egg hitting the water? Which one has to be wrong? What's wrong with A? What kind of a graph is this, Ryan? What's on the y-axis? What's on the x-axis? What is force times time? What is force times time? Impulse. Where would impulse appear on this graph if I multiply the y-axis times the x-axis, I get that equation? Where would impulse appear on this graph? What would it be? Would it be the slope? If it was the slope, what would I have done with those variables? Divide. Remember the little shortcuts I taught you? Did I times them? Where does the impulse appear on this graph? Atla. This is the impulse right here. So now, looking at the other two, you're going to ask, which of those has an area about the same as that tall, skinny one? And I think if you look at it, if you, in your mind, don't write this down, divide this in half and redraw it, you get about like that, which I don't think is enough. If you put the two triangles together and stand them upright, which I don't think is enough to cover it. I'm going to nuke that one. I think that has the same amount of area. So to explain your answer, we just did. So I took most of class. I did this on purpose because probably Wednesday of next week, you're going to have a chance to catch up on your momentum homework. I'm going to give you another lesson on Monday. It'll be a video lesson. And we'll take it from there. Your real homework is to study for the test. But for now, number 1, 2, 3 is good, 4 is good, 5 is good, 6 is good, 7 is good, although that's a review of last unit, but I'm trying to remember. I think number 8 I liked, but I don't think I agreed with the answers, so I'm going to skip number 8 right now. $12 is good. I guess that's it.